So we have our non-inverting amplifier. Non-inverting again, guys and gals, all right, means that we are feeding into our positive terminal of our amplifier. So what the gain is for here, RA plus RF over RA is basically what's going to happen when we have these two forming a potential divider. And our feedback or our gain is given by Ri plus Rf. Remember, it's the same thing over Ri, and this is called 1 over beta. We're going to see where this comes from and what it is. Now, beta is the fraction of the output that is fed back into the input. So what we have here, remember we said some of the output is fed back into your negative input. The fraction of this output, which is the decimal or the fraction, the part of the output that's fed back into the input, we call it beta. And beta is known as the feedback, not resistor, is known as the feedback factor. Feedback factor simply tells us how much current is now being fed back into our circuit. So these are our really simple diagram. So let's label this. You're going to get it labeled now. So we have, this is the very basis of a feedback circuit. All right, this is our negative. Yeah. So negative input, this is our VI, this is our VO, and that's our positive. What happens here, right? As our VO comes out, which is our output voltage, as that comes out, some comes out, and then some comes back in. And the factor by which this comes back in is called beta. Beta is your feedback factor, how much smaller your voltage is going to get. So what we're going to have, if beta is how much smaller it's going to get, the voltage in my feedback circuit is going to be beta by V naught. So let's look at our currents now, not our currents, our voltages in our circuit now. Our input is VI. Our output is V naught. This whole line here is VI, but now I have introduced my feedback voltage, as in this is coming back, being fed back into my circuit. Let's use the next current color. So this is now going to be, this new voltage is now being fed back into here. So you see this section here, we now have two voltages being added to each other. What are those two voltages being added to each other? We're going to have VI plus beta V naught. Everybody, that made sense?
Guess so.
You guess so? Remember, you're just feeding back some of the voltage out of your output into your input. So if your original input is VI and we're feeding back a little fraction of the output voltage, our new voltage going into our input is going to be greater because we now have that little extra voltage. Now, it could be greater or less because we can think about either inverting inputs or non-inverting inputs. So let's come down to doing the maths here and see what we get. Since the gain of the amplifier is AV, which is your closed loop gain, right? We know that the general equation for gain is VO over VI, output voltage over input voltage. That's your basic layout for your gain. We want to work out how to work out the gain for an inverting amplifier using feedback. So what we can do, we can cross multiply here. We're going to get V naught is equal to AV by VI. Just cross multiply, that's simply enough. But our new input is not going to be at VI after one pass, meaning if we had one pass of current, which is the very first microsecond, the VI will go straight to the VO. That's the very first microsecond. But after that, you're going to get consistently, you're going to have this happening. You're going to have, hello, I wanted a color. All right, you're going to get some of it coming out and then coming back in. So what we're going to end up getting is a different input. Our different input is going to be Vi plus beta V naught. So we're going to introduce that. So instead of Vi, which was our original input, right, this is before our current was fed back, our voltage was fed back. We now have a new input, and our new input is going to be Vi plus beta V naught. Rearranging, we expand and simplify, so you can get AV Vi plus AV beta V naught. Let's expand, right? Let's put all the V naughts on one side. So you're going to get V naught minus AV beta V naught is equal to AV Vi. Factorize out the V naught. V naught is equal to 1 minus AV beta, which is equal to AV Vi. What we do, we carry this one at the bottom here, we carry this at the bottom here, and we're going to get V naught over Vi is equal to AV over 1 minus AV beta. Now, the voltage gain of the entire amplifier with feedback is called closed loop gain. So that is what we have AV here. AV is called closed loop gain, and we can see why that was a closed loop, because our current, our voltages just get stuck in a loop. As long as this thing is operating, we're going to have voltage being constantly fed back into our circuit. All right, so that is what we have, why we call this a closed loop gain, because it is a closed loop. All right, so hence our gain, our regular gain, is equal to AV over 1 minus AV beta, where for negative feedback, beta is negative. So when we have negative feedback, the above equation becomes A is equal to AV over 1 plus AV beta. All right, so this is for negative feedback. This is for when you're going through your non-inverting. And this is for negative feedback. Now, we do have two situations to look at. In this case, the gain is less than the closed loop gain. All right, why will gain be less than the closed loop gain? Because here we have, let's just put in a value here and see what you're going to get. All right, suppose beta is a fraction, and let's see if A is equal to 1. No, if AV is equal to 1, let's see what our gain will be. All right, so it's going to be 1 over 1 plus 0.1. So it's going to give you 1 over 1.1, and that's 0.9. All right, so here you can see if AV is 1, your gain will be less than your closed loop gain. You all see that? Let's run that through again. If you just want to know, anytime they give you a proof to do and you want to make an assumption or something, just put in some numbers and you can visualize it yourself. We are saying here that regular gain is less than closed loop gain, and let's see why that happens. So if your feedback, no matter what your feedback resistor is, your feedback factor is 0.1. Feedback factor is a fraction because it's one number over two numbers added up to each other. All right, and suppose we said that our gain, hold on guys, all right, oh, why is quite up there? All right, and suppose I say that my closed loop gain is equal to 1. Let's see how much of my gain will be. All right, so you just add up your values. You'll get AV is equal to 1, 1 over 1 plus 0.1 by 1 is 0.1. So you're going to get 1 over 1.1, and that should be about 0.9, I think. Yeah, 0.9. All right, so here we can see your gain is less than your closed loop gain. Always going to be. And the next one here, if beta by AV is much greater than 1, right, then your gain is going to be 1 over beta. Let's see how we can work that out rather than us taking it for face value. So they said if beta by AV is much greater than 1. Now, why would this be much greater than 1? Remember we said gain of an operational amplifier. Guys, gain of an operational amplifier is usually how much? We did this last day.
That is the value yesterday, I remember.
Anybody remember we gave is a pretty big number, was the about range of gain in an operational amplifier. Anybody happen to remember?
Go on a while, guess, and say about what, 2000?
Nah, you just keep on saying down there, right? Ibrahim, Andy, Tila, happen to remember?
Yeah, I'm carrying off.
All right.
Yeah, my side.
Anybody remember 10,000?
It's 10,000.
Really? That's really good. Awesome job for remembering.
I know it was in the thousands.
Yeah, you continue sitting down. All right. We could be anywhere from 10,000 to 100,000. So here, even if beta is 0.1 or 0.01, right? Beta by AV is still going to be much greater than 1. Right? So what we see, if beta by AV, beta by your closed loop gain is much greater than 1, let's see how the math is going to work out. Right? So if I have AV over 1 plus AV beta, and suppose AV is much greater than 1. So suppose let's make an example, says 10,000. Right? AV. So if AV is equal to 10,000, then, no, if AV beta is equal to 10,000, sorry, then 1 plus AV beta will be 10,001. Is there much difference between 10,000 and 10,001?
That's a very big difference.
Right?
Might.
If you had to go down the road, well, not go down the road, buy something for $10,000, I seriously doubt somebody would be wicked enough to say, partner, it's 10,001, you're short by $1. Whoever has do that real wicked.
Big stuff these days, anyways.
Not a real wickedness, honestly. Or they have to agree with that. So 10,000 to 10,001 is basically the same number. Divide these two numbers divide the two numbers and tell me what you get. If you get 10,000 and 10,000, 10,001, tell me what's the difference? It's basically the same number, right? 1.0001. That's the same number. So this is where they say you can make the approximation. When beta by AV is much greater than 1, 1 plus AV beta is going to be the same thing as saying AV beta. Let me clear this up so you all can see it clearly. All right, so when beta by AV is much greater than 1, what's going to happen? So let's use the example of beta by AV is equal to 10,000. 1 plus beta AV is equal to 10,001. And 10,000 is basically equal to 10,001. So we use beta AV instead. So what we can say, gain is equal when beta AV is much greater than 1, which is almost all of the time, because the gain of your amplifier is supposed to be about 10,000. This here is going to break down and give you AV over AV beta. And we can see two things that are going to cancel out here. Our two terms are going to cancel. AV is going to cancel with AV. And you're going to be left with just beta. So what we do, all right, so let's write that down so you all can see it, even though it's there on the board. So AV over 1 plus AV beta breaks down to give us AV over AV beta, and this is going to cancel and give you 1 over beta. So the gain is 1 over beta. And what is 1 over beta? Is just the feedback factor, whatever feedback factor you have. Now, not all questions are going to give you your feedback factor. You can still go ahead and work out your gain to be minus RF over RI. And look what? This is going to be 1 over beta. So here we have two different expressions that is equal to the same thing. All right. So we did do the other day the advantages of negative feedback. All right. If we want, we could go through it again. Voltage gain is accurately predictable and constant because A does not depend on your gain of your entire amplifier, does not depend on the gain of your feedback system. A depends only on B, and this is on beta, and this is a result of your resistors. Remember, we said that the gain of your feedback system is simply the ratio of RF to RI. Those are your external resistors. This has nothing, absolutely nothing to do with your amplifier itself. What we have here, distortion of the output is reduced, and the waveform is a truer copy of the input waveform, as I said last day. I don't know if I told you all last day. All right, I think this is why I'm mixing up my lessons class and your class. All right, what happens, this is what our input looks like. Sometimes because of distortion and other signals present, because we have a whole bunch of other things involved in our circuit, our output could kind of look like this. All right, and we call this a sawtooth curve. We don't want sawtooth curves happening, and you all actually know of an example of a sawtooth curve. You all ever heard when you're listening to something, it sounds like you hear multiple of the same thing kind of blended into each other? We hear this when Mike's giving trouble. Right? Like it sounds like 2-3 people are talking together at the same time, right? As your speaker, right? And that's what happens when you have a sawtooth kind of output. That means we have a distortion in our signal, right? So rather than get this nice, smooth, sweet input, right, and we're supposed to get a nice, smooth output, we end up getting this. And this is our distortion where it, it basically looks like this, like a little sawtooth. Sawtooth indicates that there's some distortion going on, and we don't want that. We want a nice, smooth input and a nice, smooth output. Frequency response is better. We're going to see what frequency response is at the end of the session, and not end of the session, sorry, next class. And stability is increased. Remember, we said it's a much more stable system because resistors are easy to predict, they're easy to make, they're easy to manufacture. It's very, very hard to mess up a resistor. What is a resistor? It's basically a wire in a plastic coating. Not even plastic, in a ceramic coating. And we all know ceramics can go up to very high temperatures. All right, as in ceramics will melt way after the metal melts. In case you all didn't know, that little coating on all the resistors is a ceramic. All right, not plastic or something. So we have our inverting amplifier. This is where we're going to learn about how to do your actual resistance to get your actual gain by using the terms and terminology found within this topic. There are some terms that is found just alone in this topic. So let's just look and see. We have our input resistor, we have our feedback resistor, we have our output voltage, we have our input voltage, we have something here called P, all right? So let's label our stuff now. Now the currents we have here, this is II, which is your input. No, not I, we need V, sorry. So here we're gonna have VP, which is the voltage right up to P, and we have VQ, which is our positive input, and our positive input or non-inverting input has been grounded. So when grounded, what is the voltage when something is grounded?
0.
Zero. Good. All right, VQ will be equal to 0. Remember, 0 is not a number to discount. This is a very important number to give us directions of fields and directions of energies and whatnot. So this is our basic signal, basic circuit for an inverting amplifier. So if A naught is made infinite, A naught here being your open loop gain, so A naught is made infinite. And if we go back to our, let's just bear with me, let's scroll back up. All right, if we go back up to our characteristics of an amplifier, the first thing we see here, an operational amplifier is assumed to be ideal if the gain is infinite. All right, if your gain is infinite, then we have an ideal amplifier. It doesn't actually work, so there's no way we can have an infinite increase in our signal. Usually, as I just said, it's between 10,000 to 100,000, but for an operational amplifier, we have an ideal amplifier if your gain is thought to be infinite. You all hear any scrap iron people?
Like I've seen some
Yes,
scrap iron.
we hear them.
They're a low boy. Just pass in the street in the back and then come around in the front. So here we are going to assume that our amplifier is ideal, and we do something called the infinite gain approximation. By making the infinite gain approximation, we are assuming that our amplifier is ideal and whatnot. So what that gives us, we can look at some terms here that we have. In the above circuit, VQ is equal to 0. All right, VQ is equal to 0 because it has been grounded. And what happens here, VP is also equal to 0. Why would VP be equal to 0? Because as far as I am concerned, I see my input voltage and then I see my voltage here after the resistor. There's no way this voltage is so small, right, that we end up getting 0. What happens at P? P forms something that we call virtual earth. What is earth again? Earth, what's the value of voltage at earth?
0.
0, eh? That was funny. Right? That means it's at 0. And why would our voltage at P be 0? What's going to happen? Because my voltage passed through a large resistor, that is, Ri is usually a large resistor. All the resistors in these circuits are large. We're talking about 10,000, 100,000 to mega ohm resistors. Big resistors we have in these circuits. All right. So when my voltage passes through my Ri, I'm going to go from a really nice big signal, not even a very big, pretty big signal. It passes through my resistor. It's now going to become a little small signal. And what happens when I pass through my inverting input and now I feed back some of this signal in? Remember, when I run my signal through the amplifier, it gets inverted. So I now have this happening. I have a small inverted signal coming in. What's going to happen when I have a positive signal added to a nearly identical negative signal? They're going to cancel out each other. So I'm going to have this essentially happening. I'm going to have my inverted input coming in, and I'm going to have my what? And then I'm going to have pen be here, and then I'm going to have my regular input here. Now, because the regular input is slightly larger than my inverted input has been fed back. This is our feedback, right? My overall new voltage is going to be teeny tiny. When I tell you so teeny tiny, all right, it's basically near to zero. So I'm going to have this tiny little voltage that is now going into my amplifier. So what happens at P, my two voltages they combine, and they basically cancel out each other, giving me, I said basically, I'm not saying that it has been, but it is virtually Earth. There are two ways we could take this word. Virtual Earth being it's not really Earth, but it behaves like Earth, but we virtually have accomplished Earth in our signals at P, because our two signals added up together is going to give me zero. And by adding our two signals together and we get in zero, we have created an Earth point. That's why we call it virtual Earth, because it's not actually a Earth point or an earthed signal, but because our two signals cancel out or nearly cancel out each other, right? We can use something called virtual Earth. Now, virtual Earth, what it does, it allows us to be able to analyze and add our circuit current and voltages much easier. We can see where things are changing and how and why they change, right? So y'all, we okay with virtual Earth? Where we get the name from and what is happening at this point?
Yes.
All right,
No.
VP is practically zero. We're not saying it is zero, because if I have zero voltage going into my amplifier, what is amplifying? Nothing, right? But we are
Zero
making
is
this. Yeah, but you can't increase zero. How you gonna multiply zero? Tell me,
easy by zero. You get two zeros.
Jabari. Sit down. Remain sitting down. Right? So because we have an infinite, we made the assumption of the infinite gain approximation. That means if we take this really, really little tiny voltage and we run it through, with our amplifier, it is going to get magnified to a signal that we can read and use and whatnot. Um, Hold on just now. I'm gonna pause this. Okay, back. So that's virtual. This is basically a point we're going to use for mathematics to do comparison in numbers. So in the above circuit, VQ is zero, which is our grounded non-inverting input. VP is also zero because we have created a virtual earth point. And VP is actually very, very small. It's going to be to the scale of microvolts. Now, a microvolt multiplied by 100,000 or a million is going to give us a value we can use in a circuit. So, but it's therefore taken as zero, because anybody here has a microdollar, or they have no money, right? Unless it's Zimbabwean dollars. But that's the next story for next day. Or Venezuelan bolivars. All right, so it's taken as zero, even though it is now not grounded. So what we do have now, we have two currents to look at. This is a different way of deriving our gain for our inverting amplifier. That's what we're doing right now. Let me just get the circuit back down here for good reference. Nope. Right. So let's zoom back in here and see what we have. We have, why am I using this yellow? I can't see that yellow. So VI, V out, RI. So you're going to just use the same things over and over, and you know what they're talking about. VQ, VP, P. Right. So we want to look now at our currents in our circuit. And the currents in our circuit will be our I1, which is our input. These scrap iron people coming back, so let's hear them just now. And we have our output being our output voltage. Now, in an amplifier, we are not changing the amount of electrons in our circuit. The only way we can change current in a circuit is either by creating a parallel circuit and different resistors, or by adding a power supply. Our input current is equal to our output current. What we're doing here is just changing the voltage of our input signal to our output signal. So let's see what will our input current be. Our input current, they all did really loud, you know. I can't hear myself.
Don't miss we in you.
Yeah, but I know you can hear myself. Right. Right. So I naught will be, you know, V is equal to IR. So I will be equal to V over I. So for input current, it's going to be VI. Remember, we have two voltages. We have voltage of VI, which is our input voltage, and we have our next voltage, which is VQ, and that is going to be 0. So it's going to be VI minus 0 over RI. So that's our input current. Let's look at our output current. Our output current now, what it is, it's going to be 0 minus V naught. Why is it 0 minus V naught? Because our output current is both of these happening here. We're going to have our I2, these two values coming in. And since we have our voltage at P being 0, or approximated to 0, you're going to have 0 minus V naught. Why is it being minus? Because inverting, right? It's going to be negative value, so our V naught is automatically a negative value. So this over RF. So we end up with minus V naught over RF. So let's compare our terms right now. This is I1 and this is I2. Both of them are equal to each other. So all we have to do is invert and multiply to get our gain. Our closed loop gain, AV, is given by V naught over VI, which is minus RF over RI. So that is the actual way if you were to take current into consideration, how you get the gain of your amplifier. If you wanted to take voltage, as we saw voltage before, further up in the handout, there's a next way to do this derivation. So how do you know which derivation to give when they ask you in a question? Now, when they just tell you to derive the gain for an inverting amplifier, we use the one from before. Right? So we go ahead and use this one at the top here. Right? We go ahead and use this one at the top, which is what we did the last day. This is our gain, where we just look at the voltage in and out and we get our stuff. But when we talk about using the infinite gain approximation, anytime they talk about using either virtual earth right, or your infinite, okay, or to use your infinite gain approximation, they want to look at you using this derivation, this type of derivation, where we look at our two currents with taking the virtual earth into consideration. If they're not asking about virtual earth or infinite gain approximation, we use the other derivation. But honestly, both of them are going to give you the same thing. But Anytime they tell you to use virtual earth, you need to include looking at how your voltages break down to zero. So if I were you, honestly, if I were you, I would just learn this derivation and you're good to go anyway you take it. This is the better derivation because it takes into consideration we have a point where our voltages cancel out each other because of the negative feedback. Non-inverting amplifiers. Oh, I think we are finished. Class is done. All right, it's 11:26. All right, so class is finished there. So what we're going to do, we will stop here. And next day, which is Tuesday, we will go ahead and do the non-inverting amplifier and finish out this handout. Summing amplifier part is really easy. All right, so this should take us like half an hour in the next day to finish the handout, and then we are going to start. No, then we have to finish up the stuff like bandwidth and how frequency changes in an amplifier. And we'll finish it here. We're going to spend a day and something doing questions. I'm going to give you questions in each topic. So you're going to know how to approach them and you'll get an assignment on them. So let me stop the record.